Hello everyone, today we're going to be going over the June 2025 Algebra 2 Regents exam. In this video, we're going to be focusing on the short response sections. So we're going to be covering part 2, 3, and 4 in this video. A link to this test can be found in the description of this video if you want to follow along at home, alongside a video going over part 1, or the multiple choice section of this exam. That being said, we're going to go ahead and start off with number 25, which says that the data collected showing the depth of water in the bay during the 24-hour period are shown in the graph below. The depth of the water can be modeled with the trigonometric function in the form of a sine pi over 6t plus c. Estimate the value of a to the nearest integer. So in this case, the kind of anatomy of this formula is that you have a, which is going to be your amplitude, times the type of trigonometric function, either sine or cosine. And inside of here, you have b times t, or your x, where this is your frequency. And then you're adding c, which is your midline. Okay, so essentially, you see that a wave will oscillate or change between two different values. So here we go up to 25, then we go all the way down to 5, then we go up to 25, and then we go down to 5, and then we go back up to 25. Obviously, the point cuts out, but this graph will continue to go up there. Okay, so essentially, this amplitude tells you how far up and how far down this graph will go from a certain point. Okay, and essentially, because this is a sine function, it's going to start passing through the midline. Okay, so you have two different types of trig functions. You have a cosine, which starts at its maximum or its minimum, and then you have a sine function, which starts at its midplane. Because this is a sine function, the first point will lie on its midplane. So let's say that the midplane here is the x-axis. What that means is this graph will go, a certain amount of units above the x-axis and a certain amount of units below. That specific amount of units is the amplitude. So in this case, we understand that the first point here is at 15. So the midplane is 15. And then this graph will always go the same unit above and below 15, or the midplane. So to get from 25, or to get to 25 from 15, we went up by 10. Okay, and then to get from 15 to 5, we go down by 10. So we see here how we're oscillating from 10 by 10 up and then 10 down, which is going to be our amplitude, right? So we can say that A is equal to 10, since the midplane of the graph is 15, and the graph has minimum and maximum values of 25 and 5, right? So A has to equal to 10, we estimated the value of A, and then we explained it by saying that the midplane of the graph is 15 and that the graph has minimum and maximum values of 25 and 5. We could also say that 25 minus 10 is equal to 15, which is the max. And we could also say that 15 minus 10 is equal to 5, which in this case is our minimum. So essentially, we showed that we understand where this graph is centered around, 15, where the line y equals 15, and that we're going 10 units above and 10 units below, which is our amplitude, okay? Number 26 asks us to algebraically determine the solution to the equation below. So in this case, I have a square root of x minus 2, so I'm going to have to, at some point, get rid of that square root. Now, whenever you have a situation like this, you want x's on both sides of the equal sign, right? So I'm going to subtract x on this side, and it'll be clear why soon. So now I have x minus 2 is equal to 4 minus x. And the reason why I did this is because I'm going to have to square both of these sides. And it's a lot harder to square x minus 2 plus x, right? Imagine having to multiply x minus 2 plus x by x minus 2 plus x, right? It would just be a big mess. So if I got rid of that x by moving it over to this side, I can now easily square both of these sides, okay? So x minus 2 squared is just going to be x minus 2. It's that simple. Why? Because when you square root, it cancels out, okay? So that cancels that side out, but this side I'm going to have to evaluate. So I know that whenever I have a minus b squared, that's equal to a squared minus 2ab plus b squared. In this case, a is equal to 4 and b is equal to x. So in this case, I have 4 squared, or a squared, 4 squared, which is 16, minus 2 times a, or 2 times 4, times x, which is going to be minus 8x. And finally, it's going to be plus b squared. If b is equal to x, then b squared is just x squared, okay? So if you didn't want to do that, you could have also just written it out like this and then drawn the arrows of what you're going to multiply. But now you have x minus 2 is equal to 16 minus 8x plus x squared. And now what you can do is you can move everything to one side. So I'm going to add 2 on both sides. I get that x is equal to 18 minus 8x plus x squared, and I can subtract x on both sides, and I get that 0 is equal to 18 minus 7x, sorry, minus 9x, right, because we're adding on to that, plus x squared. And then I can rewrite that as 0 is equal to x squared minus 9x plus 18. And now I can go ahead and factor this out, right? So remember, you always just write x squared in the front, okay? So now I'm looking for two numbers that are going to multiply into a positive 18, but add into negative 9. And those two numbers are going to be negative 3 and negative 6. Negative 3 times negative 6 is equal to positive 18, but negative 3 plus negative 6 is equal to negative 9, okay? So now I can write that 0 is equal to x squared minus 3x minus 6x plus 18. And from here I can factor this out. So I'm going to take out an x here because they have an x in common, and I'm left with x minus 3. And here I'm going to take out a negative 6, and I'm left with x minus 3. I can combine both of these into one parentheses, x minus 3. I can combine both of these into x minus 6. And I get that x minus 6 times x minus 3 has to equal to 0. And if I want to find the solutions, I need to see what values of x make this whole thing equal to 0. In other words, you take whatever's in these parentheses and you set it equal to 0. So x minus 6 is equal to 0, and x minus 3 is equal to 0. So that means that x has to equal to 6, and x has to equal to 3. Now, if this problem didn't involve a square root, you could move on with your life. But because this involves a square root, you always have to check whether or not these answers actually make sense. So for example, if I were to plug in 6 into this equation, right? The square root of 6 minus 2 plus 6, right? Is that equal to 4? Let's verify this. So the square root of 6 minus 2, well, 6 minus 2 is 4, and the square root of 4 is 2. Then you add 6 to that. Is 2 plus 6 equal to 4? No, because that's 8. 8 is not equal to 4. Now, you didn't make a mistake in your math. It's just how it happens that whenever you're dealing with a square root function, you're going to have two answers, and one of them is going to be what we call an extraneous solution, or one that technically satisfies the equation when we get rid of the radical, but doesn't when we put that radical back in, okay? So in this case, we have to reject 6 and say that x equals 3 has to be the solution here. And if you plug in x equals 3, this side will equal to 4, and this side will equal to 4, okay? So number 27 asks us to factor this expression completely, so we're going to have to combine all the like terms here. Again, we have x minus 1 squared, so I'm going to rewrite that as x squared minus 2x plus 1. Over here, I'm going to distribute the 5, so that's plus 5x minus 5, and here I'm going to just slap on that minus 6. Okay, now I can combine like terms. I have negative 2x plus 5x, so negative 2 plus 5 is positive 3x. Over here, I have positive 1 minus 5, so 1 minus 5 is what? That's negative 4, and then negative 4 minus 6. Okay, when we combine that negative 4 with this minus 6 over here, we get minus 10. So I can rewrite this as x squared plus 3x minus 10. Okay, now we want to factor this expression. So what two values can multiply into negative 10, but add into positive 3? And that's going to be positive 5 and negative 2, okay? Plus positive 5 times negative 2 is equal to negative 10, but if you add it, it's equal to positive 3. So we can say that x squared plus 5x plus 2x minus 10. Right, we split this into 2, and now we can factor out the left and the right side. So here we can take out x from both of these. We got x plus 5. Here we can take out 2. We'll get x. Sorry, this has to be minus 2x. Sorry, this is minus 2x, not plus 2x. So then here we can factor out minus 2, and we get x plus 5. Remember, you need to have the same term in both parentheses. So now we can combine both of these parentheses together, combine these into one parenthesis, and we get this expression factored out completely. X minus 2 times x plus 5, okay? So number 28 says the results of a survey of the students at a local high school regarding the topic, what do I relax, are displayed in the table. Sorry, what I do to relax. Okay, I was reading that, I was like, there's no way that makes sense. What I do to relax, and those results are displayed in the table below. If a student from the survey is selected at random, determine the exact probability that the student claims to relax by listening to music, given that a person is female. So here's the key word, right? Given, first of all, probability is what we call part over whole. So the trick here is you just need to figure out what the part is and what your whole is. Whenever you read the word given, right? Given blank, whatever comes after that given is going to be your whole. So given that the person is female. So obviously over here we have females and males. Anyone in this column is a female, okay? So given that the person is a female means that we're looking at this probability only if that person is female, okay? So in this case, our total is going to be 87, is going to be all the females, right? So 87 plus 94 plus 21. So my total or my whole is 202, right? Now I need to figure out my part. So what is the probability that a person relaxes by listening to music? So now my part, out of all of the females, right? Given that that person is a female, so looking at only the females, which or how many of them claim to relax by listening to music. So looking only given, when you read given, you should box in what is given, right? So this entire row right here relates to females. So we're not even considering the males right here. Okay, and given this, how many of them listen to music? Well, 94 of them listen to music. And here they want us to find the exact probability. So do not convert this into a percent, okay? 94 out of 202, or you can simplify it in your calculator. 94 divided by 202 is equal to 47 divided by 101. 47 over 101. Both of these would have given you full credit. You would have gotten a point taken off if you converted this into a decimal, because the exact probability is always a percent. It is always a fraction, right? So you want to keep it as a fraction. All right. Number 29 says the graph y equals f of x is shown below, and the cubic function has a leading coefficient of 1. Write an equation for f of x, okay? So here's the trick. This is easier than you think it is, right? First of all, we know that the leading coefficient is 1, okay? And I'll get into that later. But also, we can always rewrite an equation in terms of its zeros, okay? So in this case, we just need to focus on the zeros. Remember that we can always factor an equation out. For example, if we have like x minus 3x plus 10, right? We factor that out to be like x plus 5 times, x minus 5 times x plus 2. These two are equal ways of writing these fractions. Of writing these polynomials out, right? But if we looked at a graph of this, we could see that it passes through the point -5 and -2, like so, right? So we can technically derive this factored out version just by looking at the zeros of the function, right? So over here, we see that the function passes through the point -1, -2, -3, okay? So here's the thing. When x is equal to -3, f of x, or the y value, is equal to 0. So that means that this has to be a factor. In other words, all you have to do here is just write an expression that's equal to 0 when x is equal to -3. So that's x plus 3. So the first factor here is x plus 3. That's the first thing that you write down, okay? Because when we plug in -3, -3 plus 3 is equal to 0. So our first order of business is to write down x plus 3, okay? That's the first thing. Now, there are more zeros here. Specifically, there's a 0 over here, and something is special about that, right? First of all, it's equal to 0 when x is equal to 1, okay? So what's an expression that I can write that's equal to 0 when x is 1? Well, we can write x minus 1, because if I plug in 1, 1 minus 1 is 0. But what makes this special is that it bounces off of this 0, right? It doesn't pass through like it did with x plus 3. Whenever you see that it bounces off the x-axis, you just square it. And here is my cubic function, right? Remember, we're just going to have to write down x plus 3 times x minus 2 squared. And cubic means that the highest power here is to the power of 3, and that should make sense because we're multiplying x times x squared, okay? And the leading coefficient is 1, so we know that we don't have to assign any value in front of these parentheses, right? So we can just write that f of x is equal to x plus 3 times x minus 2 squared, okay? So don't let a problem like this confuse you on the regents. All you need to know is how to write the x-intercepts, or the points at which the graph crosses the x-axis, in terms of x, right? So that it makes x equal to 0. That's all you have to do here. And again, if this function had even more zeros, right? For example, if it, decided to go back down and pass through this, no problem. You would just write an expression that's equal to 0 at that point. So if this point was like 9, you'd write x minus 9. And then add that to your function down there. You don't even have to expand this. You can just leave it here in a factored form. Okay, number 30 says given f of x is equal to 2/3 x plus 6, write an equation for the inverse function of x. So whenever you see f raised to the power, what seems to be f raised to the power of -1 x, that's not raised to the power of -1 actually. That's just called the inverse function, and it's just the kind of like looking at a function inside out. So the way that you find the inverse function is the following. We know that f of x is equal to 2/3 x plus 6. And we know that f of x is the same thing as saying y equals. So we can write that as y equals 2/3 x plus 6. Now, the inverse function is kind of like an opposite day, right? This function gives you, if you put in the y values into this function, it'll give you the x values. So it's kind of flipped. And to find the inverse function, you just flip the x and the y. So because there was a y here, I'm going to replace that y with an x. And I'm going to say that x is equal to 2/3. And instead of saying x is equal to 2/3 x, I'm going to say it's equal to 2/3 y plus 6. So essentially, you just flip the positions of x and y in your equation. And now you solve the equation for y. Okay? So what I can do here is I can say that x is equal to 2 times y divided by 3 plus 6. I can subtract 6 from both sides. So now I have x minus 6 over 1 is equal to 2y over 3. Remember that this is a whole number, so it's automatically over 1. And now I can cross multiply. So I have 3 times x minus 6 is equal to 2y. And then I can expand this by doing 3 times x to get 3x minus 18 is equal to 2y. And I can divide both sides by 2 to get 3 over 2x, or just 3x minus 18 over 2 is equal to y. You can simplify that if you want into 3 over 2x minus 9, but you can also keep them above or over the 2 if you want, right? So that's just the right answer. Just make sure to always flip the x and the y when you're finding the inverse function and know what it is. All right, so number 31 says on the coordinate plane below, sketch at least one cycle of the function, okay? So what is a function? Oh, sorry, what is a cycle? I hope you guys know what a function is, right? It's it's a relationship where every x input has one and only one y output, okay? So one cycle is pretty much the distance it takes for you to go from peak down to the dip and back up to the peak, okay? Something like that, right? So one full cycle of going down, reaching the minimum, reaching the midline, and then reaching your starting point again, right? So it's start to end, all right? So one cycle occurs within the period. So a function has a frequency and a period. The period is the distance it takes for it to go and reset itself, okay? So for example, if I have this function right here that starts off at the midplane, goes up to the 0.5, goes back down to the midplane, goes down to its minimum of -5, and then goes back up to its midplane where it started. This is one complete cycle. And if this took 2 pi, a distance of 2 pi to complete, then I know that my period is 2 pi. Okay? So hopefully that makes sense for you guys. Remember that a cycle is when you go from start to end. And don't confuse it like this, right? Don't say, oh, well, technically wasn't our start position the midplane, so isn't this one bump technically a full cycle? No, you have to go up in addition to down, okay? So yeah, this is what a cycle looks like for a sine function. But in this case, we're looking at a cycle for a cosine function. So how is that different? Well, a cosine function is different because it doesn't start at the midplane, right? It starts at its maximum. So in this case, this cosine function, because it's not negative, will start at its maximum. If this was negative 4x, it would start at its minimum. And from its maximum, it goes down, right, to the midplane. Then it goes down to its minimum, back up to its midplane, and then back up to its starting point, back up to its maximum. So this cycle will be from the maximum to the maximum, okay? So that's the shape we're going to look at here. Now, let's remind ourselves of the anatomy of this formula again, right? We know we have A, which is my amplitude, how far up or below the midplane I'm going to go, times my trig function, which is either going to start at the maximum or the midplane. In this case, we know it's going to start at the maximum because it's cosine. And then here we have B, which is my frequency, times x, okay, and then plus c. So notice here there's no c, and whenever you don't see plus a number, just assume that we're adding 0, and if we're adding 0, that means my midplane is the x-axis, okay? So this function will go 1, 2, 3, 4 units above, and 1, 2, 3, 4 units below the and 4 units below the midplane, which in this case is just the x-axis. So 1, 2, 3, 4, 1, 2, 3, 4. So that's it. That's how much we're oscillating by. And we know that because this is a positive cosine function, we're going to start at the maximum, okay? And now we need to figure out the distance it takes for us to return back to that maximum. And we're going to calculate that by taking 2 pi and dividing it by our b, right, or our frequency. So we know that period is equal to 2 pi divided by the frequency, okay? So that's it. So in this case, we need the period because we need to know how long it takes, how long it takes for us to return back to that maximum. So in this case, the period is just 2 pi divided by this b value, which is my frequency, which is 2. 2 pi divided by 2 is pi, so I know that my period is pi. So by the time we hit this point pi, we will then be back at this maximum over here. Now, the way that a wave function progresses is in equal steps, right? And there's technically 4 steps that happen here. Our starting point, then we go down, we visit our minimum, then we come up to our midplane, and then we visit our maximum. So our wave looks something like that. But if we just put this, we would get a point taken off because we didn't label the other points, right? We need to label our x-axis fully. Remember that the distance between this point and this point is equal to the distance between this point and this point and this point and this point. So in other words, the different stages of this function, right, going from up to midpoint, midpoint all the way down, down all the way back up to the midplane, they're all happening in equal increments, okay? And we see that there should be a point here, and there should be another point here. So what we can do is we can just divide pi by 4, or always divide your period by 4 to understand how much you need to increase by. So pi over 4, that's going to be my first, it's going to be my first point over here. So this is pi over 4. Okay, then over here, this is going to be pi over 2, because if we add pi over 4 plus pi over 4, we get pi over 2. Okay, if you simplify that, because you get 2 pi over 4, which is pi over 2. And then finally, we're going to add pi over 4 plus pi over 4 plus pi over 4 to get 3 pi over 4 as the x-axis, or the point right here. So here we have 3 pi over 4. And now this is one complete cycle of the function, okay? We found our period, which is the distance we need to travel to get back to that maximum point, because we're looking at a cosine function. That's positive. We know that we're going 4 up, 4 above, and 4 below. And then we know that each one of these increments is happening in equal steps. So we're equally dividing this period into four chunks, right? The period divided by 4 is pi over 4, so each tick mark represents an increase by pi over 4, okay? So number 32 says, in a recent online contest with a large number of randomly selected human players, the computer player won 67% of the time. The game design company claims that the computer player can beat humans 70% of the time. The company runs a simulation of a large number of games with the same number of human players, assuming that the computer wins 70% of the time. The simulation is approximately normal with a mean of 0.705 and a standard deviation of 0.045. Does your contest result provide evidence to contradict the designer's claim? So essentially, the person who designed this game said that the computer should win 70% of the time. And someone at a tournament complained. He was like, hey, the computer only won 67% of the time. So you're going to have to run a statistical test to see whether or not this is normal or not. And when you're seeing whether or not something is normal or not, on the Regents, you're always looking whether or not it falls between -2 of the standard deviation and +2 of the standard deviation from the mean. Okay, so in this case, we know we have a mean, or an average win rate of 0.705. So this is over here, 0.705. Okay, and then we know our standard deviation is 0.045. Okay, so we know that 2 times the standard deviation, adding it, is going to be 0.09, and then subtracting it, we're going to get we're going to subtract it by 0.09. Okay, essentially, what happens between 2 times the standard deviation minus the mean and 2 times the standard deviation plus the mean is that 95% of the data falls between this range. Okay, so if our data falls outside of this range, that means that it's a part of the 5% of data that isn't fitting our model. Okay, and if this game happened to be a part of that 5% of data, then this evidence would contradict the claim, right? It would say that, hey, this machine did not accurately perform like we were promised to, because it got a value that only happens 5% of the time. Okay, so remember, 95% of the data exists between this -2 and this +2 of the standard deviation, and that if your data point exists outside, that means that it will contradict the designer's claim, or that it will confirm your hypothesis. Okay, so what is 0.705 minus 0.09? Well, it's 0.612. Okay, so this is 0.612, and then 705 plus 0.09 is 0.795. Okay, and I made a mistake here. This should be 0.165. So now I know that the lowest normal value that we could have gotten during this game was 61.5%. And the largest win rate we could have gotten here was 79.5%. We know that 67% falls between this range, which means it's within the 95% of data. So no, this tournament was not like a crazy, 1 in a million chance. This was a standard regular tournament. It's not special. So does the contest provide evidence that contradicts the designer's claim? The designer claims that 95% of the data falls between here, right? 67% falls between 61.5 and 70. What does that say? That's 79.5%. So because it falls between the 95% range, it does not contradict the designer's claim. So we can say that no, it does not contradict. And to contradict means to disagree with. Contradict the designer's claim, as 67% falls within the 95% confidence interval of 61.5% to 79.5%. Okay, so as long as it falls between that range, it's acting normally, and the designer's claim is supported. Okay, now we're going to move on to part 3. It says, or it asks us to solve algebraically for x. And it asks us to express our answers in simplest a plus bi form. Okay, so what we have over here is we have 2 over x is equal to 2x plus 3 divided by x minus 4. And what we can do here is we can always cross multiply. So whenever you see two fractions equal to one another, always cross multiply. So to cross multiply, we multiply the numerator here by the denominator here. So that's 2 times x minus 4, and then we just write down the equal sign. So that's equal to, again, the denominator times the numerator over here, x times 2x plus 3. That's all. Just make a figure 8. So we're multiplying this by this, and then this by this. So now we can just expand these parentheses. So now we have 2 times x, which is 2x, minus 2 times negative 4, which is negative 8. And that's equal to x times 2x, which is 2x squared, and x times 3, which is 3x. Okay, so now we can combine this all to one side. So I can add 8x on both sides. Sorry, this should actually be minus 4, not minus. Sorry. 2 times negative 4 is negative 8, not negative 8x. I made a mistake there. Sorry, guys. So we could add 8 to both sides. So we get that 2x is equal to 2x squared plus 3x plus 8. And then we can subtract 2x from both sides. And we get that 2x squared plus x plus 8 is equal to 0. Okay? So now we've essentially gotten rid of these two fractions and combined this into one equation. Okay? From here, I want to solve for x. Now, remember, they want our answers to be in a plus bi form. Whenever you see something as an a plus bi form, that means you can't factor it out normally. There's no numbers that multiply into positive 8 that add into positive 1. So whenever you see a plus bi form, just know you're going to use the quadratic equation, which is negative b plus minus the square root of b squared minus 4ac over 2a. Okay, so this is your a term, a different color. This is your a term. This is your b term, the number in front of the x, and this is your c term, the number without an x. So even though it looks like there's nothing in front of this b, it's actually an invisible 1, okay? So this is going to be negative 1 plus minus the square root of 1 minus 4 times a, which is 2, times c, which is 8, okay? And then down here we have 2 times a, which is 2 times 1, or 2, okay? Sorry, 2 times 2, or 4, guys, right? Because a is 2. To avoid mistakes like the ones I just made, I usually like to write out what a is equal to. So a is 2, b is 1, and c is equal to 8. So from here, we can then go ahead and simplify this. So the way I like to look at this 4ac, I like to put a parentheses around it, just so I don't get confused with the subtraction sign. So 4 times 2 is 8, and 8 times 8 is 64, okay? And then 1 minus 64 is equal to negative 63, okay? So now this is negative 1 plus minus the square root of negative 63 divided by 2, okay? Sorry, divided by 4, guys. Divided by 4. Why? Because remember, a is 2. 2a is 2 times 2, which is going to be 4 down here. Okay. So from here, the issue is we cannot have the square root of a negative number. So the way that we avoid that issue is by remembering that whenever you have radical a times radical b, you can combine the multiplication underneath the radical sign, right? So from this, I know that negative 63, the square root of negative 63 doesn't exist. So to kind of avoid or ignore the fact that we have a negative symbol here, I know that, well, 63 times the square root of negative 1 is the same thing as saying the square root of negative 63, because you can just write 63 times negative 1 underneath the same radical sign, which means you could do the opposite. You can split this back up into these two multiplications, but remember that I is equal to the square root of negative 1. So the square root of negative 63 is technically the same thing as saying 63 times I. But that's not the only thing that we can change here, right? Technically, that's how we get our bi, but remember that whenever you have a radical, the Regents wants you to express it in simplest form. So you have to think, are there any perfect squares that go or come from root 63? Well, we know that 63 is equal to 7 times 9, right? Radical 63 is equal to radical 7 times radical 9. And we know that radical 9 is equal to 3. So we can simplify this into 3 times radical 7i, okay? And now we can write this as negative 1 plus minus 3 times radical 7i over 4. Or, because we technically want this in a plus bi form where the two are separated, we can say that negative 1 over 4 plus minus 3 root 7i over 4 is our answer, okay? Make sure you write the I outside of the radical symbol, okay? And that's all you have to do here. So there was just 2 steps. The first step was to combine everything together. The second step was to use the quadratic equation. And if you want to consider this a third step, you just needed to simplify that radical by taking out the I and by taking out a perfect square. Never forget this point, or never forget that part. So number 34 says a highly selective college reports that the mean score earned by accepted students on the mathematics levels 2 subject test is 750 with a standard deviation of 20, and the scores are approximately normally distributed. Given this information, determine the interval representing the middle 95% of student scores. So in the previous part, we already know what the middle 95% entails, and that's going to be the mean plus or minus 2 times the standard deviation. So we know that the mean is 750, and we're going to add or subtract 2 times the standard deviation, which is 20 from that. So we have 750 plus 40 and 750 minus 40. And that's going to give us a interval. So the middle 95% interval is 790, where you actually start with the lower term first. So is 710 to 790, and that's all you need to get full credit here. Okay, just literally just do 2 times the standard deviation and you add and subtract that, right? So it's pretty easy. Now the second part says to the nearest whole percent, determine the percentage of accepted students who scored 760 or less. So in this case, whenever you want to determine the percentage of someone who scored more or less, or the percentage of like a certain outcome, and you're given the mean and the standard deviation, you're going to use your calculator, right? Essentially, what you're going to do is you're going to consider the standard deviation, or the standard distribution curve. Distribution curve. We know that this curve is always centered around the mean, which is 750. Okay, and essentially the area under this curve represents everything that could happen. So essentially this curve goes all the way from 0 to the maximum score. Okay, and the area underneath this curve is 1, right? Because 100% of the students will score at least a 0, between at least a 0 and the maximum score if you're taking this test, right? There's no other scores you can get. But what the problem wants us to do is to find the percentage of students who scored 760 or less. So instead of taking the area of this entire curve, we want to know the percentage of students that scored all the way up to 760, but no more. So we're taking the area all the way from 0 all the way up to 760, and the calculator will do that for you. So we'll go into our calculator, and we'll go ahead and we'll hit second vars. Now we have normal PDF and normal CDF. So we'll scroll down to normal CDF. You absolutely need to know this calculator function. And we'll press enter. Okay. Now it asks us for our lower and it asks us for our upper. And this is why I gave you this example here. We want to know the percentage of students who scored 760 or less. So the lowest score that we're looking for is going to be way below 760. It's going to be a small number, close to 0. And the calculator already put in a small number there, right? -1 times 10 to the power of 99, right? Very, very small number, close to 0. Essentially, this is close to 0. If this number isn't already typed in here, what you could do is you can just do 1 times 10 to the power of negative 99, right? Something like that. And from there, what you can do is you can plug in your upper bound, right? So we're looking from anything really close to 0, if not 0. And then our upper bound is the maximum value that we want to stop searching for. So the calculator is going to start searching for the percentage of students that scored a 0, right, or very close to 0, and it's going to start looking at higher and higher and higher scores, but we want the cutoff to be 760. We don't want to see any other student that scored above a 760, so my upper bound has to be 760. Then this symbol right here is the mean, which is 750, and this circle with a hat is the standard deviation, which is 20. So if I go ahead and press paste, I can see that the normal CDF gives me a value of 0.6914. Okay, and we want it to the nearest whole percent. So 0.6914 translates into 69.14%. And if we want the whole percent, we're rounding to this decimal right here. Because 1 is less than 5, it's just 69%. Okay, so the calculator will then consider that 69% of the students scored between 0 and 760. 0 being my lower bound and 760 being my upper bound. So that's how that function works. Now, in order to show work, all you need to do is just show the regents what you plugged into your calculator. So you just type in, or you literally copy it off the screen of your calculator, CDF, or you just write normal CDF, 1 times 10 to the power of negative 99, comma, 600 760, comma, 750, comma, 20. And you close the parentheses, you say that's equal to 0.6914, and then you conclude that 69% of students score at least, or score no more than 760, or score 760 or less. That's all you needed to do here. So number 35 says for c of x and for d of x, determine c of x times d of x minus d of x to the power of 3 as a polynomial in standard form. So all we have to do here is just multiply these two out. So we know c of x is 3x squared minus 4x plus 7, and we're multiplying that by x minus 2, okay? And I'll write that in the opposite way to make it more easy for ourselves. Okay, so x times 3x squared is 3x cubed. X times negative 4x is negative 4x squared. X times positive 7 is positive 7x. Okay, here we have negative 2 times 3x squared, which is negative 6x squared. Negative 2 times negative 4 is positive 8x. Okay, remember it's negative 2 times negative 4x. So we have to slap the x on there. And here we have negative 2 times positive 7, which is negative 14. So now let's combine like terms. Right, here we have a minus 4x squared and minus 6x squared. So we have 3x cubed minus 10x squared plus 15x, because we combined these two together, minus 14. Now, from here, we just have to subtract d of x cubed. So we know that d of x is x minus 2. So we'll multiply x minus 2 by itself 3 times. I already know that x minus 2 squared is equal to x squared minus 4x plus 4. And I'll just have to multiply this by x minus 2. So x times x squared is x cubed minus 4x squared plus 4x, right? I just multiplied over here. And then here I have to multiply by negative 2. So minus 2x squared plus 8x minus 8. So that's what that's equal to. So now let's combine like terms. So negative 4 and negative 2x squared. Okay, negative 4x squared minus 2x squared is going to be minus 6x squared. And then positive 4x plus 8x is positive 12x. And then we'll slap on the minus 8. So here we have x cubed minus 6x squared plus 12x minus 8. Okay, now remember that there's technically a bracket around here, which then gets converted into a parentheses pretty much, right? Because we're subtracting the result of d of x cubed, so we have to put a parentheses around there. And remember that there's a minus sign outside of our parentheses, so we have to distribute it before we can combine these like terms. So now we have 3x cubed minus 10x squared plus 15x minus 14, and then we'll do negative 1 times x cubed, which is negative x cubed, plus 6x squared, because negative 1 times negative 6x flips the sign, minus 12x plus 8. And now we can truly begin to combine like terms. So here we have 3x cubed minus x cubed. So that'll give us 2x cubed. Over here we have minus 10x squared plus 6x squared, which is minus 4x squared, because negative 10 plus 6 is negative 4. Over here we have 15x minus 12x, which is positive 3x. And over here we have negative 14 plus 8, which is going to give us negative 6, okay? So that's going to be my final answer over here. That's what it's going to be equal to. And the standard form just means that it's in order of decreasing exponent. So the highest exponent here is 3, followed by 2, followed by 1, followed by 0, okay? So this is standard form. So number 36 says that Christopher works for a defense contractor and earned $85,000 his first year. For each additional year, he will receive a 2.5% raise. Write a geometric series formula, C of n, for Christopher's total earnings over n years. So if you don't know what the geometric series formula is, it's found in your reference table down here. It's a1 minus a1 to the power of rn is over 1 minus r, okay? So that's a1 minus a1 times r, which is your rate, to the power of n, which is the amount of time, divided by 1 minus your r. Okay, so in this case, a1 is the first term, or your initial. So in this case, he earned $85,000 his first year, so that's going to be his initial. So C of n is equal to 85,000 minus 85,000 times r. Now what is r? R is the rate, okay? So in this case, he's receiving a 2.5% raise. So his account is increasing by 0.025, okay? You cannot write 25% here. You need to convert it into decimal. But don't just write 0.025 here. That's actually incorrect, because 0.025 is how much he's increasing by. Whenever you do a raise or an increase, you're going to add that percent to 1, okay? That's 1 plus 0.025, or 1.025 That's the increase here. And that's going to be to the power of n, and that's going to be divided by 1 minus your rate, which is 1.025. Now, if he was decreasing, right, if he was losing money at a rate of 2.5, you would have to do 1 minus that rate. But whenever you're increasing, you just add 1 to it before you plug it in, and that'll get you full credit for this part. All right, so this next part wants us to find his earnings over the first 10 years of employment. So this series, remember, you're not using a sequence. Don't use the formula for a sequence. Use the formula for a series. This series pretty much tells you the sum of all of his earnings for a given amount of time, right? So we want to find all of his earnings, or the sum of all of his earnings for the first 10 years. So guess what? We'll just plug in 10 wherever n is, because n is the number of years. So we know that C of 10 is equal to 85,000 minus 85,000 times 1.025 to the power of 10 divided by, that's terrible, guys, oh my god, divided by 1 minus 1.025. And I already plugged it into my calculator here. If you press enter, you figure out that he earns 952, or that C of 10 is equal to $952,287.45. Okay, but that's not your answer, because they want us to raise it, or to find it to the nearest $100. So this is to the nearest dollar, this is to the nearest $10, and this is to the nearest $100. So we need to round it to this number right here. So that means that C of 10 is actually equal to $952,300, right? That's how much he earned over that time period, okay? And that's going to be the correct answer here. So finally, moving on to the last question, or part 4, it says that cesium-137 decay can be modeled with a formula AT is equal to A null times e to the power of kt, where at represents the mass of the remaining grams after t years, and a of 0 represents the initial mass. A sample of 500 grams of cesium-137 takes approximately 60.34 years to decay to 125 grams. Use this sample to determine the constant k to the nearest thousandth, okay? So essentially we have this formula. A of t is equal to a of 0, which is the initial mass, times e, which is Euler's number, to the power of k, which is the constant I'm trying to solve for, and t. Now, how can I solve for k here? We'll plug in values. I know that my sample initially weighed 500 grams, okay? So I know that it initially weighed 500 grams. So my a of t is equal to 500 times e. E is not a variable, it's a number, right? It's Euler's number, it's a special number, so you don't plug anything in for e. Then that's e raised to the power of k, which is what we're trying to solve for, times t. Now, if we read the problem further, we started with 500 grams, but we ended up with 125 grams. So a of t gives you the weight after time. So technically, a of t is actually equal to 125 grams, because 125 grams remain from that initial 500 times e to the power of k times 60.34, because that's my t, that's my time. So in other words, 125 is equal to 500 times e to the power of 60.34k. Now to solve this, I want to get rid of the coefficient in front of e. So I'm going to divide everything by 500, okay? Always divide everything by 500. You're left with 0.25 is equal to e to the power of 60.34k. Now, notice how I'm trying to solve for k, and k is kind of locked inside of this exponent place here. The only way that I can get k down from that exponent position is if I get rid of it, get rid of this e, or take the natural log of both sides. For example, ln, or the natural log of e to the power of x, is equal to just x. So if you take the natural log of e, it automatically cancels out that e and brings that variable down from the exponent slot. So in this case, if I take the natural log of e of 60.34k, I'm going to have to do that to the other side. So I'll take the natural log of 0.25 as well. But when I take the natural log of e to the power of 60.34k, guess what? The natural log and the e cancel out, and you can bring down this exponent. And now you have 60.34k is equal to the natural log of 0.25. And from here, you can just divide both sides by 60.34 to get k. So then k has to equal to, let's calculate it, the natural log, which is ln here, of 0.25 divided by 60.34. Okay, and that's going to give you negative 0.229. So k is equal to negative 0.2297. They want us to round it to the nearest thousand, right? So rounding k to the nearest thousand, well, this is the tens, this is the hundreds, and this is the thousands. So we're rounding it up from this number. So k has to equal to negative 0.230, right? Because once you round up this 9 turns into a 0 and actually rounds this in the 100th place up. So that's what k is equal to the nearest thousandth, okay? Now they want us to use this k to write the function a of t that will find the mass of a 500-gram sample remaining after any amount of time in t years. So now we already know that a of t is equal to the initial, or 500 grams, times e to the power of k. Now we know that k is negative 0.230, and we're going to multiply that by t. So now we have the complete equation with all of the variables plugged in, or all of the constants plugged in. This is my initial, this is my decay rate, or my r, and this is the time which I'm going to change. And using this information, they want us to graph a of t on the graph below from t equals 0 to t equals 150 years. I want to graph this equation in my calculator is what I meant to say. So here I have 500 times e to the power of negative 0.023, or 0.0230, doesn't matter, x. And when I hit graph, I'm not going to see anything, and that's because I'm too zoomed in. So if I go into window, that'll allow me to change my parameters, right? And notice how my x is my t, or my time. And I'm looking through a range of 0, starting at 0 years, all the way up to 150 years. So my x min is 0, my x max is 150. The same thing goes with my y min. My minimum value for y should really be 0, right? Because that's when the sample is fully decayed. And my maximum y should be the starting point, right? Or slightly above the starting point. So my maximum y, the highest that my y-axis can go to, well, I start off with 500. That's my initial. So I know that my first point is going to be at the point 500. So I'll just go a little bit above 500, like 550. And now I'll hit graph. And now I can actually see my function as well, right? Just perfectly out here, okay? So I'm going to have to eventually copy that down onto this graph right here. And in order to do that, I need to assign my axes. So I know that the graph goes all the way up to 500. So I'm going to put 500 up here. And then I'm going to count by 50 going down. So this is 450, 400, 350, 300, 350, 250, 200, 150, 100, 50. Don't know how that happened, guys. Right there is 50. And then finally over here is 0. So I'm counting up by 2 until I reach 500 all the way at the top over here. And I already know that my first point at t equals 0 is 500. I have my axis set up here, so now I'm just going to go ahead and set up my x-axis. So I'm just going to go up by 15, so sorry for that. So I have my x-axis labeled over here, and now I just need to look for points to graph. So what you can do here is, because each one of these points goes up by 15, you can go ahead and press second table, and then change your delta table, your triangle table, to 15. And what this will do is every time you press the down arrow and move down on your table, it shows you the next 15 points, right? Or the next point that increased by 15. So I'll show you what I mean by that. So if I press second table, or sorry, second graph, I get my table. And over here, you see that my x's go up by 15 because I set that delta to 15, okay? So anyways, here we have 0 at 500, so we'll plot that point here, and I'll get back to you when I plot all the points. So over here, I've plotted all the points down, so I just have to connect them with a curved line. Don't connect the points like this. Make sure you don't have like jagged edges. You want to make one continuous line going down. And I really suck at this because I'm doing this online and not on paper, but your graph should look something like that, okay? And because you're graphing it over a set range, you actually don't need to put arrows on either end of your graph, okay? And finally, I just want to label this as a of t is equal to 500 times 500 times e to the power of negative 0.23 t. Okay, so now this says use a of t to calculate the average rate of change in grams per year from t equals 0 to t equals 60, and then round your answer to the nearest 10th. So the average rate of change is the slope between 2 points. Okay, so the first point is t equals 0. Remember, t is my x. So the first point is 0 comma 500, and the second point is going to be 60 comma whatever it is at that point. And over here my table says that it's equal to 125.79 at 60. Okay, so the average rate of change is just the slope between these 2 points. So we'll do 60 minus 0, right, over 125.79 minus 500. Okay, so I can go ahead and calculate this in my calculator, right? I have 125.79 minus 500 divided by 60 minus 0, and that gives me negative 6.23. I want negative 6.23, and again I want this to the nearest 10th, which is just negative 6.2. And remember that the average rate of change always has units. So the units of the y-axis here is obviously going to be grams, and the units of the x-axis is going to be years. So this is 62 or 6.2 grams per year. Okay, that's going to be my answer over here. Remember, it's the slope between 2 points. Whatever unit is in the y-axis is the y unit, or the unit that goes on top, and whatever unit's on the x-axis, which in this case is time, but more specifically the amount of years, goes in the in the denominator of that fraction, right? So remember, average rate of change always has to have units. And now they want us to explain what this value means given the context. So you can say that the average rate of change is the average amount that you were changing by, so in a given interval. So you can say that between the time 0 years and 60 years, on average, the sample, or the mass of the sample, was decreasing by 6.2 or negative 6.2 or 6.2 grams per year. The reason why I didn't say negative 6.2 grams per year is because it's already implied that it's negative because it's decreasing, right? And that's it. That's the entire short response section reviewed. If you have any questions, please feel free to let me know in the comments down below. Thank you guys for watching. Again, if you want the full review of this exam, I already uploaded part 1, so check that out in the description.